This is simple thing, a similar thing it is saying here, right? So here we have wealth, right? Here we have happiness. These all data is present. These are all trained data, let's say, and this is the best fit model I have created based on like theta naught plus theta 1x, right? And here, what I'm doing, I'm adding one more theta 2 x square, theta 1x, and theta naught, the similar thing. And it here might be theta, here it will be x cube, or here theta 4 x to the power 4, and you can write it like 3, and all the other these things will come here. So what will happen? So when this model complexity, you can say that this polynomial, when we are increasing it, our model is becoming more and more complex. All right. So in that case, what will happen? Initially, your training data, training error will be, it will slowly come down here. In this case, here it is the point, like the training error. But you go further down here. In that case, your training error is reducing further, and your test data, this is like the unseen data, like prediction error on new data, here it is also reducing. Like when you will like learn more and more signals from your train data, it will train more, right? It will error on your test data, that will reduce, it will come to the point. But when you start like learning all the signals with the noise what you have in your train data, then your test data, the unseen data, their error starts coming up, right? But your train data error will always go down and down and down, because you are training more and more on this data, right? So this is what actually here the problem happens. So here the first model here, the first model, let's say we will say it has high bias. All right. And the third model, this is third model, in that we have high variance. But second is balance of both. How we say that? Because you see, from this point, actually in test data set, error starts going up, right? So this is the balance, right? Here it is the balance of bias and variance. So what do you mean by bias now? Bias is basically how well how well you are learning the signals from a trained data set. That is actually bias. How well you are learning, learning signals from trained data. Okay. And when I say high variance, so why this is like high bias? Because here you see the error. Bias is also an error part, which we'll see as a mathematical form in the next slides. So what we'll see here, when we say high bias here, so it means here you see the error is high. In this case, if you see model predicting error in this case, so it is high. So slowly, when you reduce the bias, it will come down, and your trained data set, it will learn more and more signals from your trained data set. So your like bias will get reduced. But one thing will happen, your variance will start going up. So what is the variance? Variance is basically how much you are able to predict on a test data, right? So why I am saying this third as a high variance? Because in this case you see, when I have this third model, then on unseen data I am not able to predict it correctly. This error is going up for a for a new data. So that is why it is called high variance. So bias, again I'll tell you, bias is like how well you are taking signals from your trained data set, right? And variance is like how well you are able to predict on a test data set. Okay. So what will happen, like you will have to reduce your bias, but as well as you have to keep the variance intact also, right? Because when you are learning more and more signals, you are going from 1 to 3, your error on trained data set will go down. Slowly it will go down. But you see, after some point, after this point, on unseen data it is going up, right? So your variance is actually getting higher and higher. So this you can say as a variance part, where maximum separation is happening, this separation is happening, it is increasing again. So what you have to do, you have to learn signals from a train, as well as you have to keep the variance low, so that your model will predict correctly on your test data also. That is basically this whole graph means. All right. Now, if I say like model complexity, I gave you one example of degrees of polynomial. So I was increasing degrees of polynomial error. I was keeping 1 degree, and then I did second degree and third and fourth. This can be like represented by number of features. So here, let's say, this is a 2D graph, right? This is a 2D graph. So here I cannot show this, but yes, in one time, instead of theta, theta naught, sorry, theta naught plus theta 1 x plus theta 2 x1 x2 theta 3 x3, you are adding more and more features, so it is becoming, your model becoming more and more complex. So that can be a model complexity also. So it should not be just taken as, okay, this degree of polynomial will only show me like my model complexity is going up. You are adding more and more features, your model complexity is going up. And in case of like when you will learn a tree based model, so in that, like if depth is increasing or number of iterations increasing, so like this we think of. So just don't get confused with this, like only square we have to put. It might be like more and more variables you are adding. As you are adding more and more variables, you are giving more and more signals which you have already in your training set to the model, right? And if you add redundant like 100 variables, and out of those 90 variables are redundant, then it will not predict correctly on your test data, although it has taken all the signals from your test train data, but it will not predict correctly on your test data. So this is all about bias and variance, right? So we will go more into like what I have described here. In supervised machine learning, an algorithm learns a model from trained data, and goal of any supervised machine learning algorithm is to best estimate the mapping of f to the output y given the input x, right? This is the simple thing which we always do about right here. If we talk about, this is the a mapping of y with x. So this is what here it is written: input data x and output variable y. So now to say like for an error, like whenever we are doing validation and all, everything, everywhere we are seeing, we will have some parameter, we'll have some metric. In that we will say, okay, like our model is showing some error. An error we divide in three parts. First is bias error, second is variance error, and third is irreducible error. Okay, so bias error, I was telling you how much how it is like taking signals, how much signals from trained data it is picking up. Okay, and variance error is mostly like how well you are predicting on test data. All right, this is the this is the way you think of. Bias is how well you are taking signals from your train data, and variance like how well your model is performing on test data. Okay, this is how we think of, right? And irreducible error are those noise which you cannot reduce, like whatever complexity you add, there will be some irreducible error associated with that, and that will be always be there. Like your model cannot be 100% perfect. Like it will not be 100% perfect. There will be some noise whenever you are like predicting, creating one model. There will be a irreducible error which you cannot reduce. Okay, so by I will skip this part. I'll just go to directly to the uh, mathematical representation, so it will be easy for you to understand. This is like the similar same thing it is saying with the thing like model will have high bias, pays very little attention to the train data. Like it gets very little single signal from your train data, and oversimplifies this model. Like, because I am just taking the let's say first degree, it should take the 2 degree, then it will be the more more robust, and more it will be predict good on my trace data. So these kind of things are there. Like when it is very simple model, then like high bias will be there, and like it will always lead to high error on train data and test data, right? Then I have like variance like it will give high variance pays a lot of attention on to train data. Like when we have like fully fitted on our train data, then it becomes like then my variance goes up. The same thing which I was talking about, this is written here. All right.